Just to give you a quick overview of what the next hour is going to look like. I'm going to give perhaps 5-minute, 10-minute talk on molecular representations real quick, and then we're going to go right into actually installing RMG onto your laptops, and that will conclude with that before lunch. So hopefully that should give us enough time to get RMG installed on the laptops. But before we get to that, we wanted to give a quick talk on molecular representation in RMG. Like I said, these are just a couple of short slides for now so that you guys understand the basic concepts before we actually play around with RMG, because you'll need to know how RMG treats molecules so you can input it into your input file. Later on, I will update these slides with a little bit more detail that will be more helpful, but for now, I just want you guys to understand the very basics. So of course, for RMG to function, it needs to know basically, well, what molecule you're talking about. Of course, there's usually tens, if not more, different names for different molecules, and it needs to know what the structure is of the species that you're interested in for it to be able to generate these models. So we'll go over a couple of different things about how RMG handles species and what you need to know about it. There's kind of two distinctions that you need to know at this phase. One would be molecules themselves. For example, in your input file, you'll say what the initial starting species are in your system. And then there's also this functional group idea. You probably won't have to deal with this as much unless you really delve into the code or you want to understand more about how RMG got its predictions. But this relates a lot to how it determines which reactions are possible, per se. So there's a couple different ways you can represent a molecule that we want you to be familiar with. Adjacency list. This is the way that RMG handles everything internally. You could give a molecule many different ways, but it will always convert to an adjacency list. And I'll talk about that in a second. But probably more user-friendly, if you will, is this thing called a smile string. Of course, this is not something that we've invented. These are very common. You can look these up on Wikipedia, but they're basically a way for you to write a little bit of text to tell the computer what molecule you want. And then there's these things called inchy strings, or inchy keys, which are an attempt, because smile strings are not unique. So there'd be multiple smile strings corresponding to one molecule object. Inchy tries to overcome these things. They're a little less user-friendly because of that, but there's some advantages to that as well. So the way that a molecule gets represented in RMG, for example, here's a little bit of a snippet from your input file. So like I said, when you're running RMG, you need to tell RMG what your system is, what's there initially in your model. So you would open up your input file and you would create something like this. We'll go over exactly this later. But you'll give it a label, which is just for your needs. It could be any name. Once again, there's tons of names for compounds. So what you're going to do is you're going to give it something like a smile string. And in the background, RMG is going to convert this into something called an adjacency list. So for methane, its adjacency list is kind of like a matrix that's, well, in this case it's a list. There's also adjacency matrices. But it's describing all the atoms that are in my molecule, how those atoms are connected to each other, and other properties of atoms. So as you'll see, we have 5 atoms, as you can see from the bottom of this number. We have 1 carbon atom and 4 hydrogen atoms. And if you look to the far right, it'll tell you how these atoms are connected to each other. So for example, this carbon atom is connected to atom number 2, which is a hydrogen, and a single bond. And you can kind of get the idea from here. It's also connected to 3, 4, and 5, which are also hydrogens. And there's these other properties here that you see. Right here, the U tells you the number of unpaired electrons on the atom. The P tells you the number of paired or lone paired electrons on that atom. And C tells you the charge of the atom, which in most cases will be 0. So the reason why this is important is there are some actual molecules where a smile string representation, you actually can't really represent it well as in the same way. So sometimes you'll actually need to create an adjacency list and edit things like the number of unpaired electrons, especially if you care about the spin states. For example, O2, oxygen, right, is actually not 2 lone pairs. It actually has 2 unpaired electrons in it. It's a biradical. You actually can represent O2 just fine in smile strings, but sometimes you actually do care about the electron configuration. But most of the time, like I said, if you're going to be the user and you're going to enter something in an input file, most of the time you'll just be getting used to smile strings. Here you can see it's just a simple C to kind of give you the idea. Ethane, which is BCC, and it's kind of a linear representation. We'll let you look that up on Wikipedia, but most of the time I'll be using smile strings. So I think this pretty much just kind of describes the same thing here. So this, of course, tells you the atom numbers, the elements, pretty much everything I just described there. There's one other type of thing that, like I mentioned, there's functional groups. We also call functional groups adjacency lists. They're very similar, except you'll have things like R, not H. You saw in Alon's presentation earlier where we talked about trees, where we're trying, if we don't know the rate of a certain reaction, we're trying to match it to something that we think is best known to. So you try and get more and more specific. So this functional group is saying that the first atom can be any atom, R could be any atom. The exclamation point, for some of you coding, is a not. So any R that is not a hydrogen. So you'll see functional groups like this, but otherwise they work in the exact same way as an adjacency list does. You'll get these different specific types of atom types instead of just normal carbon. We can get into that later. But you also have these functional group representations. One final thing that is also included in the adjacency list I've got to mention, that's also really important, is the multiplicity. This is just the spin multiplicity of the system. So for most of your ground state closed shell species, it has a spin of 0, and so 2s plus 1 gets you to 1, which is a singlet. A lot of your radicals have a spin of a half, so 2s, 2 times a half plus 1 gets you to doublet for most radical species. So you also have to include this a lot for the adjacency list in RMG. This was taken from previous slides made by Hiro, which is a former visiting scientist in a group. Like I said, I will go back through and update this, but if you were to look at this again, you probably can figure out most of what you need to know, but I'll add more detail into this later. But the biggest thing I want everybody to take away from right now is just the idea of how RMG represents molecules as an adjacency list, how those things are connected to each other, and that probably your most useful friend is this thing called a smile string for defining molecule objects in your input file. Are there any basic questions on this before we get into the installation phase?
So just for questions, in case of methane, there's U0, P0, C0, and I saw U is impaired and P is impaired, and what is C?
C is the charge, so there's no formal charge on that atom.
So everything is 0 for impaired, and charge?
Yes, so what it's saying is all the valence electrons are in these bonds. So of course, carbon would have core electrons, and you don't include those.
If your molecule was, your species was inert, would you say reactive false?
Yes.
Okay.
Yeah, so I didn't want to mention that. We'll get to that later when we talk about RMG, but you can add species in to your input file, but you don't want them to generate reactions with that species with anything else in the core, so you would set this flag equals false. We'll talk about how that relates to the rest of the input file, but yes, that's exactly right. To repeat the question for the online viewers, sorry. The question was this reactive flag here. You could set this to false if it was an inert species. So if you go to rmg.mit.edu, I just want to show you something real quick before we conclude for lunch. So if you go to our website and you go to the far left-hand tab, you'll see something called Molecule Search. If you click there, there's a lot of different features. You can look up different properties about a molecule. You can look up its thermochemistry. And this is a good way for you to get used to what smile strings are, adjacency lists, etc. So, like I said, you could draw the molecule. For now, I'm just going to enter in the name, benzene, and immediately it recognizes it, and I know it recognizes it because out pops its adjacency list. You can see here that we have carbons, we have 6 of them, with 6 hydrogens, and you can see the connectivity between the atoms. Interesting, in this representation, we're actually doing single bond, double bonds alternating between the carbons of benzene, but there's actually a benzene bond type that's supported in RMG so that it treats the ring as aromatic. For whatever reason, the website pulls up this version of benzene, but RMG can actually support the aromatic version as well. But you can even draw the molecule to make sure that you have the right molecule. Here, once again, we're doing alternating single double bonds, so that's the representation we get. but you get a lot of information out of it. You get its molecular formula, molecular weight, its NG string, if you're curious what that is, and then you'll see its SMILES string here, which I don't know if I can write on the board, but let's see if we can blow this up. So of course, benzene is a ring, but like I might have mentioned earlier, SMILES strings are a linear thing. So the carbons, of course, tell you that those are the carbon atoms attached to each other in succession. The equal signs tell you that it's a double bond attaching this carbon to this carbon instead of just a single bond. But there's one other thing that we have here, which is that we have this one's labeled as C1 and this one's labeled as C1. That tells the SMILES string that these two carbons are also connected to each other. So that's what actually is completing the ring here. Let's do another one real quick to get a little bit more familiar. I think this. Hurt. Thank you. So this is T-Butyl Bending. You can see some other things going on here. Once again, we have the carbon label, number labels 1 here, telling that these carbons are closing the ring. We also see we have parentheses here, and that tells you that there's a side chain off of this carbon. So this carbon is connected to this C1, but there's two side chains, one that has one carbon off of that, and another side chain has another carbon. So you can do branching that way. You can even represent radicals. So let's do like the simplest radical. I'm going to actually type it in a species identifier. You can type in the SMILES string. So here you see the SMILES string. You can see that it is.
Yeah, that's not right.
That's not right, though.
It's an H's on it. Inside the bracket, you need H2.
Oh, yeah, sorry. So you can, SMILES is trying to figure out the proper number of hydrogens that need to be added to make the valency work out. But you can also explicitly write out what you want by including it in a bracket. So you can say just 2 hydrogens, so it knows that there's a radical on that carbon. I won't go over this much further. I'll let you guys kind of play around on your own. As you can see, you can figure out the SMILES strings and the adjacency list and how those all work together. But this is more than just that, of course. If you go here, you can also do things like search species thermochemistry, and you can find out what we have about this species thermochemistry in our own databases. For example, this is a result of a thermo library called DFT QCI Thermo, and you can see what we think this species has for heat of formation at 298 Kelvin. You can even get the thermo in as a NASA polynomial, which we'll talk about later, but if you use ChemChem a lot, this is, of course, very useful. But I just wanted to show off this tool real quick, get you guys a little more familiar with how RMG would handle species, especially if you have a species in an input file that you have no idea what the SMILES looks like. If you can get at least the name, or if you can draw it, then you can figure out what it SMILES from the website.